As of 2017, the population in the United States has grown to be around 325.7 million. Population growth has been increasing in a linear pattern since the 1900s. With the rapidly growing population, the demand for farm-grown foods has been on the rise. However, this brings to attention a variety of issues. The Earth is composed of 70% water and only 2.5% of all water is freshwater. Currently, water used for irrigation accounts for nearly 65% of our world's freshwater withdrawals. As the population continues to grow, we start using more water. Additionally, in order to grow crops, we also require vast amounts of soil. Although many may not realize, soil is a non-renewable resource, and as we start producing more crops, we use more soil. Soil is formed through the process of weathering and chemical decomposition. Rocks chemically react with water and other acids in order to form weaker rocks that fall apart more easily. This process is prolonged and tedious, much like the formation of fossil fuels. In order to form approximately 2 centimeters of soil, over 500 years is needed, and about 3,000 years is needed in order for that soil to become fertile. Soil is mainly comprised of a combination of organic matter, such as plant residues, microbial mass, humus, and minerals. Soil organic matter is crucial to many aspects of soil, such as water retention. A major property of soil contributing to water retention is the particle size. Particle size and water holding capacity have an indirect correlation, meaning that as the particle size decreases, the water holding capacity will increase. When particles are smaller in size, it results in the surface area of the soil to increase. When this occurs, it becomes easier for the soil to hold onto water, which results in higher water holding. Another key component used to determine the water retention is the porosity. In order to have a high water holding capacity, it requires the soil to have adequate amounts of organic matter. SOM and water retention in soil have a direct relationship. This is because SOM promotes the creation of aggregates, which are groups of soil particles bonded together. The overuse of soil, however, results in the loss of organic matter, which causes soil infertility. This information brings to attention the problem that this experiment is addressing over water use and soil degradation. The intended purpose of the experiment will be to test the different growth mediums to determine which one will have the best water retention properties and which one promotes the most efficient plant growth. The hypothesis states that if coconut coir is used instead of soil, then the moisture levels will be greater in the coir plant instead of the soil plant. For my methodology, prior to experimentation, a program was coded to determine moisture levels of the plant. To do this, an easily accessible program called Arduino Uno was used to create the code. The code was written using C++, which is a simplistic high-level programming computer language similar to Java. For my actual experiment, 30 13-centimeter plant pots were used. The first 10 pots were taken and 340 grams of potting soil were placed within each pot. The first set of plant pots represented the control group in the experiment. Another set of 10 pots were taken and 340 grams of finely ground coconut coir were placed into the next set. For the final set of plant pots, 1,700 grams of coir and 1,700 grams of soil were taken together and combined to form a uniform mixture. The coir and soil mixture were taken and 340 grams were placed into the remaining 10 pots. The last two plant pots represented two distinct variables which were tested in the experiment. After placing the growth mediums in each pot, 5 fenugreek seeds were planted. Although the experiment was not to determine which growth medium was optimal for plant growth provided additional support for my hypothesis. After the coir and soil were placed into designated pots, each plant was given exactly 240 milliliters of water each day in the morning. Moisture measurements were taken 2 times for each pot. The first time, measurements were taken 3 hours after the pots had been watered. The measurements were then taken again 3 hours after the first measurement had occurred. In order to collect the data, each plant pot was taken individually and the moisture sensor was pushed upright into the growth medium. The moisture levels were then displayed on the computer screen and each value was placed into an Excel sheet. The plant heights were also measured using a centimeter ruler and were placed into the Excel sheet as well. To determine the correlation between plant growth and growth type correlation statistics were used. A scale from 0 to 1 was used to determine the overall correlation of the data. The data points were plotted on a regular Cartesian graph and a linear regression equation was evaluated. Using the data derived from the experiment, t-tests were taken to determine whether the data results were statistically different. Below, the table displays the t-tests. When looking at the statistics taken from the plant test with plant sets 1 through 10 and plant sets 11 through 20, we obtain a t-value of 0.2844 and a critical value of 1.9773. The values show that there's no significant difference between the variables since the critical value is much higher. Therefore, it can be determined that both plants with soil and coir gave fairly similar results. In comparison with the t-test results comparing the soil and coir, the t-value comparing the soil and coir combination and just the soil was also significantly lower than the calculated t, with a value of 0.3108. This also shows that there was no statistical difference. The last t-value was calculated comparing the coir and the soil and coir combination. The results showed a calculated t-value of 0.7592, also providing to be lower than the critical t. The table above shows the average plant height and statistical analysis of each growth mediums tested. The heights of each set of 10 plants were averaged to compare the difference in heights. We can see that the soil and Coir mixture had the greatest plant growth with 6.133 centimeters. The previous three charts were then used to determine the correlation between plant height and growth medium. Out of the three regression lines, the only one that came close to showing a correlation was the Coir plant. The Coir plant had the lowest p-value of 0.05885, which indicated there was more correlation between the Coir than any of the other two variables. The graph below shows a bar chart comparing the moisture levels before and after the plants were taken. The measurement of the moisture levels before the plants is watered is shown in blue. Coir and both the Coir and soil mixture tend to have a higher value, which indicates less moisture present before watering. This data can indicate why the soil and Coir had the greatest growth. The graph above shows the percent change in moisture between the three variables. There was few exceptions in both the soil and combination mix where the soil had lost mixture. The Coir plant, however, only had one minor outlier. The moisture means among the three variables show that Coir had a mean of 170.009 and soil had a mean of 196.624, and the combination mixture had a mean of 160.534. Apart from the moisture levels, the plant heights among the three variables also varied. When looking at the plant height from the soil and Coir mixture, the plant heights are significantly higher than the soil mixture. The Coir and soil combination had a mean of 6.133, whereas the soil only had a mean of 3.92. The means were very close. The mean of the Coir was only 0.133, less than the soil and the Coir mixture. Based on the data, we can conclude that the hypothesis of the overall experiment was not supported. In furthering the findings of my experiment, a larger sample size could be used in order to maximize the accuracy of the results, along with using other various growth mediums.